comments and notes on your essay, and I posted the study guide for final exam. Please review them. Obviously, some questions are from prompts are from previous writing assignments that we have. They may appear in a different form or concentrating on different sub-questions in the final exam question sheet. But those topics are topics that you have to study well and get ready for the final exam. One thing that I noticed by reviewing the second writing assignment, I found that a few of the students, they didn't have any idea about the prompts. Probably they read the prompts just when they attended class last Wednesday, and they read the prompt for the first time there before writing the essay, specifically in a question related to skeptical philosophies. I immediately realized that some of these answers were directly coming from the internet, from the source from the internet. And it is obvious why, because we studied skeptical philosophies in the context of history of science. Obviously, there are philosophical ideas about skepticism and its general philosophical aspects. But in Deer's book, we directly connected skeptical philosophies into science in discovery of the absolute truth, to Descartes' ideas. And since Descartes was central in this period, then we mostly discussed Descartes and skeptical philosophies in the mid-17th century. So when you don't read the assigned readings and books, and you rely mostly on whatever you find online, then obviously it creates problems. I saw a few grades were as low as 170, 180 because of just this not using the assigned readings and relying on online sources. Anyhow, that was a short introduction how to get ready for final exam. Again, please read the assigned readings and then try to have a big picture first about the story, a big picture about geocentric model, a big picture about, I don't know, Copernicus discoveries and heliocentric model, a big picture about Newton's role in scientific revolution, and so on and so forth. And after that, after creating this big picture in your mind, then you go and explain the details. So what was Newton's impact on his contemporary science and science after Newton? What were the characteristic features of Newtonianism or Newtonian culture? And the same thing for other scientists or scientific developments that we already discussed. Okay, last time we stopped here in the last few lines of this slide, talking about the impact of Newton on not only physics, but also on science in general and philosophy of science. Newton is considered the summit, the climax, the most important outcome of the scientific revolution, because he established a culture, he established a way of thinking in science, which continued after him. And it started from finding the basic rules, the fundamental laws of everything around in a mathematical way, based on measurements, based on calculations. His idea is a combination of all previous uh, achievements that we had in science. Newton studied Descartes very well, and in Descartes' philosophy, in Descartes' mechanical universe, you find particles in motion. In Newtonian version of this approach to understand universe, you find that, okay, this particle is made up of mass, and then this you have to find out about the magnitude of this mass, and then it moves, find out about its motion, and then now you have three laws of motion, and you know about the existence of, for example, gravity in the vicinity of the earth. And then you combine all these things and then find out how does a projectile, a cannonball, travel on the earth, or how does a particle of a very, very, very small particle uh, moves inside other particles. When we are talking, for example, motion of a particle inside another medium like water. The same thing in air. What items are defining the motion or the the change that we have in a medium like air? Okay, then you analyze it. What this air is. They didn't know anything about molecules and atoms that time, but they knew that this air exists here. It is a fluid and it has a density. And then including whatever we know about materials with different densities, you find out, okay, how circulations happen in air. How does hot air rise and cold air sinks? And then you invent a new concept which is called convection. Now connected to other discoveries that Newton had about different substances. So questions like this, um, it's not directly from Principia, but similar statements you can find there. Okay, you walk in a beach, uh, you are under the same sun, the same temperature, the same atmospheric condition, but the sand of the beach burns your feet, but water not. Why? While the temperature around is the same. Then you invent something and come up with a new concept, which is called, I don't know, specific heat capacity. So you find out that solid objects like sand or iron, they don't keep heat inside. They release heat immediately. They get warmer faster and they release the heat faster. But on the other hand, water takes a longer time to absorb heat and it takes a longer time to release the heat. Then apply all these things, you find out that on the land you have air. Air warms up pretty quickly and then its density decreases and that hot air rises. Then uh, cold air takes its place, a kind of convection happens, and it causes what the majority of these uh, atmospheric turbulences or what happens in our atmosphere we can explain based on very simple approach that we took from Newton's physics. So by applying the same thing to machines also, you can understand how does a machine work. You know that um, a steam engine, which created that was the beginning of industrial revolution, was invented by a craftsman, by James Watt, who was not a scientist. He was just an engineer, craftsman with not what call very deep education, university education in science. Uh, he just realized that by putting together these components, he could make this steam engine or improve the previous steam engines that he had. And later, we see that by using Newtonian approach, a person named Sadi Carnot in France, about 90 years after the invention of steam engine, he applied Newtonian mechanics, Newtonian physics to understand what was going on inside this steam engine. What is heat? How can you define heat? What happens in heat transfer? You boil water, and even that time we didn't have this concept, this term, we call it energy. So you warm up water, you turn it into steam, and what is inside the steam which creates that much pressure, which moves the piston inside this steam engine? And then what happens to that heat? How can you find out about the physics of the steam engine? And we see that by applying all these things, we created a brand new science in the 19th century, which we call it thermodynamics. We didn't have thermodynamics before. People obviously they knew about heat transfer, but how to scientifically study that came after Newton. And I talked about this Baconian sciences, which were sciences without having a root in classical sciences. So classical sciences were astronomy, mathematics, natural philosophy, which we call it physics, and a little bit optics and a little bit mechanics. How about new sciences that we have, like, I don't know, meteorology, about oceanography, about geophysics, geology, electricity, magnetism, thermodynamics, all of these new sciences created after Newton. And they followed actually Newtonian approach in these uncharted territories. And by using experimental philosophy, which developed by Sir Francis Bacon, that's why these sciences are called Baconian sciences. Scientists were able to invent brand new sciences. So Newton, at the end of his book Optics, uh, asked a very interesting, thought-provoking questions about uh, all these occult sciences. Let me call them occult because we didn't know anything about them. About action in a distance, about electricity, about magnetism. And then during his life and after his life, many scientists started to follow Newtonian approach and make discoveries about these fields. At the beginning, their approach was uh, qualitative because they didn't know anything about these things. Their approach was experimental uh, because they had to do a lot of measurements about the nature of these fields. For example, when we are talking about heat and heat transfer, you need a device to measure heat, the amount of heat. Okay, and you need a thermometer. When we are talking about the relationship between density of air and pressure of air, then you need a device to measure the pressure of air, air pressure. And you use that device to see that the pressure of air is more when you are at beach, and then it is less when you climb to the summit of the uh, a mountain. And then in this way, find out that there is a limit for this atmosphere, and this atmosphere has a pressure coming from its weight, and just apply all these things to understand uh, the behavior of atmosphere very well, and then you create a new science. Then we see that how these beginning sciences were connected to instrument, and they had to design new instruments. And here is the place that we see for the first time science and technology came closer and closer to each other. So at the beginning, the makers of these new scientific tools were scientists, and then we see engineers came to the scene, and they had to, for example, create a device, a measurement tool, to measure the force between two magnets, the force between two charges, and then how to measure that, how to graduate it. Again, let me give you an example to see what was the dynamism of scientific activities this period. So you make a thermometer, then it is one part of the story. You invent something, you design a device and make it. Then the second part is how to graduate it. Uh, why it is so important? Because you had to find out uh, a standard for all these measurements. Okay. Uh, Again, it is funny that in the past, when they wanted to make measurements, and they use these measurements in their trades or buildings, or I don't know, other activities that they had to set a standard. Okay, we have a unit called yard. Okay, and that yard actually was defined based on the distance from the nose of one of British kings, I don't remember, to the end of his arm. Okay, they wanted to establish a measurement unit. Now, this is king's what the distance from the end of his nose to the end of his arm, and they measured that, and it became the standard unit of measurement of length. Uh, you could use it in medieval periods, but now we are in a period that we need very accurate measurements, and we had to establish what references. Uh, Later we see that they found that, okay, size of the earth is not changing. Then we use the circumference of the earth as a unit of measurement and cut it, for example, in 40 million parts, and we call it 1 meter, not yard. That is standard unit. Everybody can understand it. So we had British units uh, like ounce, like pound. Then how about we think about an international unit? And again, they define kilogram or gram, which is, it comes from the mass of 1 cubic centimeter of water. So you define meter and centimeter, and then since water is water, H2O, pure water has its own density and mass, then you define things based on that. Now, we want to make a measurement tool for temperature. Now, what is the 0 point? How do we graduate it? What happens in nature exactly the same way all the time, which can be used as a 0 point of the free water, I'm sorry, temperature, or the graduation that we are using. Then the first thermometers that we had were graduated based on uh, say body temperature of human being, Fahrenheit, which was body temperature of majority of human beings is the same, say uh, 97. That time they thought that they can use it as 100, but now we know that there's 97, 98 degrees. Then they made this graduation based on that. So the freezing point of the water is 32 based on that, and then the boiling point is 212. But later we see that Celsius uh, invented new measurement tools. Anyhow, the entire story in this period is how to uh, uh, make all observations with accurate tools and create more and more data. And then by analyzing the data, find the mathematics behind nature. So add to this their strong religious belief that they had. Newton himself believed that God created the entire universe based on mathematics. Then when they used measurement tools or these new uh, instruments, these instruments for experimentation, and using them, they uh, acquired a lot of data. Then by playing those data, they were able to find mathematics behind that, and then discover basic laws of nature. Last time I explained about this, for example, they didn't know about force between charges, and they invented a device, invented an instrument, designed an instrument to measure the force between two charges, and then to measure the distance between two charges and correlate it with the force of between two charges. Newton's equation for gravity was what? F equals to g m1 m2 divided by this distance square. And they found that the same rule is valid in the attraction or repulsion of two charges. They discovered by mid 18th century that the force between two charges is equal to a constant multiplied by the first charge and multiplied by the second charge divided by distance between them squared. So in this way, what a mathematization of nature happened, how to understand nature based on the final mathematical rule governing in that phenomenon. So this is the period of the development of Baconian science, actually in second half of 18th century and the entire 19th century. We see that following Newtonian questions at the end of optics, it was the beginning point, but obviously they made a lot of new discoveries and new questions came, and they involved instrumentation and experimentation in their discoveries. And we see that by the beginning of, by the end of the 19th century, we had a lot of new sciences following Newtonian rules, and those new sciences uh, immediately found their way in industry, in technology, and became inseparable part of industrial revolution. For example, think about electricity, magnetism, thermodynamics, which enabled us to bring electricity to daily life. At the beginning, electricity was something happening just in the lab. There was no application for that. Little by little, people were able to invent batteries and then running electricity, the electricity that we are using. First, they were using it only for lighting, and then by development of generators and electromotors, uh, they used electricity as a source of energy, and then back-to-back inventions brought electricity in our daily life. Okay, um, so all started from uh, the revolution that happened in science in the 17th and 18th century. In Newtonian celestial mechanics, we had a number of very complicated questions. When you study physics, Newtonian physics, at the introductory level, we consider the, for example, say in gravity, the simplest problem that we have is how two objects attract each other. We talk about the attraction between the sun and the earth, and we forget about the rest of the universe. It is the simplest way that you examine gravity between two masses. But the reality is very, very complicated. Look at the solar system. Okay, we have, by that time they discovered new planets, but the story is this: the sun is at the center, okay, and planets are moving around the sun, and their distances, they have different masses, and their distances all the time is changing. So now you have a very, very complicated system that when uh, distance between these masses are changing, their gravitational pull is changing. And all the time, we have an uncertainty about the gravitational pull between the members of the solar system. Then uh, you ask this question that how come that with all these changes, instantaneous changes in the force between the planets, solar system still is working, is uh, has this order, and it is not out of order. It doesn't have a perturbation. Uh, Solving these problems was very difficult, and finally we find out that Pierre Simon Laplace, which was one of the greatest minds in um, after scientific revolution and a very good follower of Newton, he was able to solve majority of these problems and created actually a very refined and very complete form of Newtonian physics and Newtonian celestial mechanics, which became the base for uh, the further studies in both physics and celestial mechanics. And still, this book is a reference book when you want to calculate, for example, orbits of, I don't know, space probes. Okay, yeah, these are images from the Royal Society of London. Uh, Top right is the entrance of Royal Society of London, which is a new building. The original Royal Society burnt in a fire in 18th century, and then they moved another place, and finally this is the modern building that they had. I took these pictures a couple of years ago. I was there, and my favorite parts were they keep uh, some strands of Newton's hair, as you see here. You read here, I say Newton's hair here, and this is the death mask of Newton. That trip was like a pilgrimage for me to see everything that they collected from Newton, his handwritings, his books, and uh, as you see here, hair and death mask. This Royal Society of London, as we already talked a little bit about its importance, but because of the experiments that they performed there, it became, actually it created back-to-back small revolutions in different fields of science. Peter Deere, in his book, talks a lot about this air pump. And this is a very good experiment, a very good example to talk about how science developed that time by doing experiments, coming up with a lot of new questions, trying to answer those questions by new experiments, and to do new experiments was demanded to perform new experiments demanded again new tools, new what called instruments, and you see that in about say 60, 70 years, the number of devices that they invented or designed and the number of studies and experimentations that they performed there is really a lot. You have to make a list of page after page after page of all these observations and measurements that happened in Royal Society of London with different experimenters. I explained that last time that these gentlemen, these scientists, they rarely uh, uh, performed experiments directly because they were noble people. They didn't make their hands dirty, but they hired experimenters that they knew physics, Newtonian physics very well, and they asked them to do this and do that. Because of this, these experiments, and having new practical questions related to Newtonian physics, we see that when Newton was alive and after him, a number of interpreters of Newtonian physics appeared in England and on the continent. So Newton's book was very difficult. Still, if we are interested, you are very welcome to go and you can find online versions of free versions of Principia, and you read them, you find out it is really difficult to read and understand. When Newton was alive, uh, we see that a few people started to make user-friendly forms of his Principia and his optics too. So they interpreted the context and then they added examples from real life. They added diagrams and images to Principia, and uh, they added some questions and answers based on Newtonian physics. And even now, physics books that we have, they are modern versions of whatever you find in Newton's Principia. I'm talking about introductory physics courses. So this is the period enriched with experiments and interpretation of the results of experiments. One of the experiments was with air pump. They invented air pump. It has a long story, the invention of air pump, but the uh, very practical and very advanced form of air pump was invented by uh, Robert Boyle. And then new questions started here. What kind of questions? You can use your speculations and see if you can come up with these questions and find some answers for that. Okay, this is air pump. You connect it to a jar and vacuum it. Then the first philosophical question appears here. You extracted everything from inside that. Then what is inside that? What is emptiness? What is vacuum? Exactly the same question that Aristotle had, and we already talked about that. Okay, now you come up with what? In many experiments like this time and before Robert Boyle and before Newton's time, we had versions, very what call crude versions of this air pump. And when they evacuated air from a container, they found that it collapses, it breaks. Why? They discovered about the pressure of air above that. For the first time, they tried to weigh the air. Then, in the very good version of this air pump, they started to perform a lot of experiments. First, to find out about gas, about this air. Then they connected it to life science. How? They put different animals inside the jar and evacuated the air to find out what was the relationship between this air that we have and life. They put different animals there and they studied the reaction of different animals. For example, when you put a snake in this vacuum jar and a bird, the difference is drastically different. Bird dies immediately, but snake survives for a long time. So it was a new way to study the body of these two different animals. Then they involved, for example, electricity in these experiments. You know that if you rub glass against silk or a fur, uh, you create static electricity. Now, in one of these experiments, they, in majority of these electric machines, they were rotating a spherical jar, a spherical piece of glass, and hollow glass against silk. Then, in one of these experiments, they evacuated air from this jar, and then they applied it in this. They used this electric machine, and they produce electricity, but they discovered a very, very important thing. And they found that uh, when they produce this static electricity in a vacuum jar, then a kind of light appears inside. That was the beginning of a long story, which finally ended up to the discovery of electron. So this started from late 17th century, and then after invention of batteries, we applied the same thing, and we found this light in this vacuum chamber. And then finally in 1879, J.J. Thomson discovered electron. This vacuum jar glass I'm sure you remember this old TVs, big glass TVs that we had, actually using the same thing that was discovered uh, in 18th century by applying what this air pump to a glass jar, evacuating it and applying electricity to that. It creates what's called cathode rays, and these cathode rays finally found its way in what making this big TV. So you see that how uh, all these things were connected to each other, the experimentation and invention of new um, experimental tools or equipment or instruments. And to make those instruments, you needed what engineers or involving your theoretical knowledge in design process of these equipment and performing new experiments, finding new results, and trying to interpret that. In many fields, we see that it happened, and we had a lot of discoveries, not only in physics, but also in biology, in chemistry. So just we talked less about microscopes. We talked more about telescopes, but microscope itself opened a new door to things that we didn't know at all about that. Little by little, discovery about fine structure of life, discovery about cells and the importance of cell as a building block of life. Then, by making better and better microscopes, in focusing inside cell, and then finding about the internal structure of the cell. Then, from the other side, we see chemistry enters to find out about the materials inside the cell, how to analyze and then find out what is inside the cell. And you can continue this the story to find about, I don't know, heredity, about chromosomes, which obviously happened later. But everything was what connected to Baconian science, how to use experimentation to verify your ideas, how to involve instrumentation in your experiments, and then uh, improve science. This is the uh, dynamics of this period, and you compare it with what we had before. We didn't have lab for thousands of years. Scientist was uh, a passive interpreter of nature based on philosophical principles and rules, mainly coming from Aristotle. So, in one of the lectures, I briefly explained about this. Since everything was known in uh, Aristotle's philosophy, everything was categorized in Aristotle philosophy, there was no space for invention. We knew about the number of stars, we knew about the number of planets, we knew about categories of flora and fauna, we knew about even the habitable part of the world. Then there was no um, eager to go and find more because they believed that there was no more there. Why should we go and make discovery about this? And we see that one by one, new discoveries broke that image that we had from the universe. I always compare it to this thought experiment. Imagine you lived in a mall, okay, and you had everything in this mall. You had, I don't know, grocery store, you had a clinic there, you had, I don't know, a small inn, you could stay there. And You were self-sufficient there, and your entire universe was that mob. And imagine once a, a crack happens in one of the glasses or walls, and you see that, oh, this is not the entire universe, this is not the entire world that you have. There are other stuff. At the beginning, this crack was small. You were able to see a little bit of outside, but little by little, you were able to penetrate more outside and make more discoveries and find out about the real universe around yourself. The same thing happened during the scientific revolution. Before that, our universe was limited uh, size-wise, and from the viewpoint of the number of things that we know in this universe. And everything was classified, categorized, and there were explanations about everything. Now we see that by the discovery of new world, okay, it was a geographical discovery, but the first crack happens here that there was something, there was an island, and later they discovered an entire continent that nobody knew about this. Then by invention of telescope, they were able to see things that nobody was able to see before, and that was another crack. I don't know, by discovery of the celestial origin of supernovae and comets, they found that Aristotle was wrong in his uh, cosmology. The same thing when Galileo discovered about, I don't know, phases of the moon and um, sunspots or the structure of the moon. Again, they discovered that whatever they had in their scientific books, philosophical books, were either incorrect or very limited. Now you can observe more and more. By the invention of microscope, we were able to dive into very small structures and find more about that. Then this is the period that we call it the scientific revolution. So to summarize the characteristic features of um, scientific revolution, we can talk about discovery of new approach to understand nature. As I explained before, uh, how did we understand nature in Aristotelian way? Or the dominant approach that they had during the ancient and medieval period, just describe everything, describe, explain the things as they are, they exist in nature, and describe them based on what philosophical principles that you had. So you were just taking a snapshot and explaining that. Now we discovered what an experimental approach. Then uh, this experimental approach caused mathematization of nature, to understand nature based on what mathematics, based on the third line here, natural laws, based on the underlying what uh, rules, mathematics governing the function of natural phenomena. So we let me give you an example. Uh, Free fall. In Aristotle, it was just a natural movement of heavy objects toward the earth. Then now we do measurements, we do observations, and we find how does it happen, measure the distance, measure time, measure velocity, measure gravity, and so on and so forth. And this is not a qualitative approach. It is a quantitative approach with mathematics. And then by Repeating it over and over, you discover what natural laws. You find out that on the earth, free fall all the time happens based on this law that you discover. Then to perform all these things, you move from pure speculations, pure philosophical approach, you move to experimental philosophy. You perform experimentation. And that's why in the process of experimentation, you need instrumentation. And then these instruments, okay, enable you to mathematize nature more and more because you collect more and more data by these instruments. So in medieval period, it was nonsense to ask somebody, how was the weather? Okay, the answer was, it's warm or it's cold. It is neither warm nor cold. There was no number for that. They didn't need this number because the lifestyle, the way that they looked at phenomena around themselves, they didn't need those numbers. Okay, we had numbers in astronomy, obviously, but that numbers were used just to describe that moon moves from here to there. Those numbers were not related to the nature of motions that you see in the sky because they didn't know about celestial mechanics. They didn't know about forces. They were just describing, okay, the motion of a planet or moon, the sun, how far they go in a unit of time. That was not mathematization of nature. That was a description just. But now we wanted to dive and find out the underlying rules in nature, which these phenomena happen based on those rules. Gravity acts in this way, heat acts in this way, projectiles moves based on this rule, electricity works based on this rule, and you have all laws which you can express them mathematically, and it repeats the same way all the time. Now, combining all these things, and applying it to fields that we didn't know anything about them, we started to invent new sciences. As I explained in the case of, for example, electricity and magnetism. The same thing in, I don't know, oceanography. What's going on inside the oceans? What caused these old turbulences? What caused these waves? And how deep are oceans? What's the situation there? Then you apply the same thing uh, to earth science. We knew geography. Geography was one of the old sciences that we had. How to describe uh, the lands and rivers and mountains and I don't know, forests. But after Copernicus, after the establishment of heliocentric model, Earth itself became a topic of study, like other planets. So people started to study moon, map the craters of the moon. They started to study the sun. The same thing about the earth. What was the origin of the earth? Why we have these mountains here? How did they form? What was the age of the earth? How can we guess the age of the earth or estimate the age of the earth? And you see that by studying more and more, they uh, came up with a lot of um, new ideas. Like what? Uh, they found, for example, I'm just giving one example before we have a break. They discovered fossils. Okay, Aristotle knew about fossils. You can find fossils of fish on top of mountains. They knew about this. And Aristotle has this idea that, okay, this uh, mountain somehow was underwater. Very good. You could mix it with religion. We have this story of flood, which flood covered the face of the earth. You can immediately connect it. Okay, Aristotle is correct because later Bible actually verifies it. It happens that when the entire earth was underwater, so fish were on top of mountains, and then when flood ended, then you can end up to find fossils of fish there. But what do we see in 18th, 19th century to find out about uh, the dynamism of changes on the earth? For example, they discovered this is the time also which mining developed a lot, and we had a new science, technology, mining, how to find out about different ores, different minerals. And by scientific mining, they found, for example, fossils, bones, which those bones didn't match with any other species on the earth. That time they traveled most of the places on the earth. They knew about the flora and fauna of different places. But when they discovered, I don't know, a bone of 5 meters, then they ended up to this conclusion that once in the history of Earth, there were animals which they extinct and they don't exist right now. Then the question was, what happened? What kind of processes happened on Earth to end up the life of some species? They became very vigilant about uh, geology. You see mountains and uh, say rocks on the mountains, and you find out that they are twisted. You see that the layers and layers after on top of each other, okay, you have a bunch of layers of rocks and they are twisted. The question was, what force or forces cause this twist in these rocks? One of the first questions was about the age of the earth. One source was Bible. Okay, the Protestant interpretation of literal interpretation of Bible says that the age of the earth was about 4,000 years, because it's very clear. You list the uh, you use the book of Genesis, and Adam lived that much, his son lived that much, and then his son lived that much, and you add them up, reach to Abram, and then there's 4,004 years, and after that until Jesus, you have the the what called the ancestors timeline, and then during Newton's time, it was a common belief from religious side that the age of the earth was about 6,000 years. So from Adam to Jesus, and from Jesus to Newton times, you add them up, and I believe it was 6,400 something years. But scientific investigation in geology, in mining, in studying of mineralogy, they found that the age of the Earth must be very, very uh, bigger than the numbers that they had. Another scientific question, for example, appeared here. I believe once we briefly talked about this, that if flood happened, then did Noah take prototypes of animals to the ark, or the parents of all breeds and all different uh, forms of animals that we see? In other words, did he take the prototypes of or parents of all dogs, just one pair, or parents of, I don't know, 200, 300 different breeds of dogs that we have, types of dogs that we have, took all of them? The first one was more reasonable. And then to create the diversity that we see around us among the living organisms, you needed a very, very long time, not 6,000 years. Then, as I emphasize here, new sciences appeared to answer these questions, and to uh, answer all these questions, they had to do a lot of experiments. In the case of geology, they had to dig more and more, or find a pattern how to estimate the age based on the specification of living organisms they find in different layers. So this was the beginning of a scientific geology, which immediately connected to life science, to heredity, to evolution. And the question, they discovered that, okay, when they dig and go in the past, whatever was the past, because we uh, actually calculated the age of the Earth much later. We had to wait for a lot of discoveries in mostly in atomic science to find out about the age of the Earth. But putting that aside, they discovered that when they are going in the past, sorry, they could find, uh, uh, I don't know, fish, but not mammals. Then in a different layer, in the upper layer, they can find fish and, for example, lizard. Then they can find in upper layer fish and lizard and, I don't know, bird. And then in the upper layer, they can find all these things plus mammals. And it created a pattern which directly connected to evolution and history of life on the earth. So in the past in history of the earth, you could find very simple forms of life. And then you see that after a long time, they had to estimate the length of this time. You see that a little complicated form of life appears. After a long time, again, this form of life becomes more complicated. And then you had to define all these things, and you end up a new science, which is called uh, geology. And you can use the same method, the same approach to even things that we had like anthropology. The same rules you can find uh, in sciences related to, we already talked about thermodynamics, about studying of heat and electricity, magnetism, and many other scientists that were invented during and after the scientific revolution. And in this image by William Blake, he actually depicted Newton as a divine geometer, a kind of what person, a messenger of creator who discovers about the underlying geometry and mathematics of the universe. So this Newtonian approach was so successful, which many other scientists and thinkers, they tried to uh, just follow this very successful path and make discoveries in their own field. This is called the culture of Newton or Newtonianism. Adam Smith, John Locke, Voltaire, Franklin, Darwin, they tried to apply them in sociology and psychology, in electricity, in life science, how to discover the underlying laws, simple laws, and then explain the uh, uh, visible or apparent diversity in these fields just based on those simple rules. Okay, uh, in the second half of this class, we're going to watch a documentary, one of the best documentaries about Newton. There, Newton scholars explain about different aspects of Newton's life. This documentary is about uh, 55 minutes. It is a part of assigned reading materials for this class. So please watch it carefully. We're going to watch together. And at the end, we're going to discuss about that, about different aspects. I explain about different aspects of that. And then uh, it covers a part of the third book that we study. We study under the title of The Clockwork Universe. And I'll finish that book uh, on Wednesday or last session or last class and for this course. So just before starting this video, after break, obviously, uh, I just set the scene and talk about the most important uh, people in the Royal Society of London, like Robert Boyle. We just talked about his inventions, his air pump. Christopher Wren actually was the master of Newton in mathematics, and after Christopher Wren, Newton became the location professor of mathematics in Cambridge. Christopher Wren was a mathematician, an architect. He actually was designer and builder of a very big cathedral in London, Cathedral of St. John's, which uh, was the tallest building in Europe up to, I don't know, 1900s. I don't remember, but it's a huge building in London. Then we had Robert Hooke, which we're going to talk about him more, but we already uh, mentioned him because of his work on microscopic studies. John Wilkins, another scholar, mathematician, and physicist there. Sir Robert Moray, which was the first called uh, secretary of the Royal Society, and Bronker, another scholar there. These people gathered there to promote new science, new sciences, modern science, in other words. And one of the most important focus that they had, how to promote physical mathematical experimental learning. What is this physical mathematical experimental learning is whatever we explained, how to avoid being a passive interpreter of nature, but follow Bacon, what was the most famous motto by Bacon? He says that torture nature to extract her secrets. That is the physical mathematical experiments, how to mess with nature, how to design purposeful experiments and then get more data. This is the mathematical part. And the physical part is the doing experiment. And then in this way, you learn about the underlying laws of nature. Let's stop here. Let's have a break of, say, 15 minutes. And then we come back and watch this documentary and then discuss uh, the content of the document. I'll come back after 13 minutes.